Welcome to day 13. Homework is packet page 3. Make sure to be putting that on a separate sheet of paper. So our first one from the homework, you were playing around with e to the x and trying to get something that worked out pretty good for it. So you would have various answers, but here's the one that's the best. So the best would be if we had 1 plus x plus 1 half x squared plus 1 6x cubed plus 1 24th x to the 4th. And we want to think about, well, how could we write that differently? Well, 24 is really 4 factorial, 6 is really 3 factorial, 2 is really 2 factorial. The x is over 1, which is 1 factorial. The 1 is over 1, which is the same as 0 factorial. And this one here would be 5 factorial. So we're going to put our e to the x1 on our card. So on your note card, under the sine x and cos x1, let's do e to the x equals, and we're going to do 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 equals, we'll do our summation from n equals 0 to infinity. And our x's are always raised to the same as our n value, because we have n equals 0, then 1, then 2, then 3, and so on. So we'll have x to the n. And then the factorial on the bottom matches that power, so we'll have over n factorial. So we should now have 3 things on our card, and we will add 2 more of them today. So next one wanted us to find cos x in a different way by taking the integral of sine. So your antiderivative sine is negative cos over on the left. On the right-hand side, we start with our Maclaurin for sine. Take the antiderivative, so exponent goes up to 2, divide out front by 2. Exponent goes up to 4. When we divide by 4, that now becomes a 4 factorial instead of a 3 factorial. X to the 5th becomes x to the 6th. When we divide by 6, 6 times the 5 factorial gives us 6 factorial. And notice we have a plus c on the end because it's an indefinite integral. If we divide everything by negative 1, all the signs switched, and that c is still some constant. If the function is something we know a point for, so cos x in this case, then we should be able to resolve what c is. A nice value we know is that cos of 0 equals 1. So if we put in 0 for all the x's on the right, we should get back a 1, which means that our c should equal 1. So then what I did is I rewrote that right side, putting the 1 first so it matches with your powers. And notice now that is identical to what we had in class yesterday. For the third one, we wanted to find a polynomial for sine 2x by taking sine x and just subbing in 2x everywhere there's an x. And once you neaten that up, you get what's in the box. In part B, we wanted to do that a different way. Sine 2x is, from our identities, 2 sine x times cos x. So they wanted us to take a 2nd degree for cos and a 3rd degree for sine from our Maclaurins that we have for that, and do 2 times the sine part times the cos part. And then when we neaten it up, we get the part in the box there. Part C wanted us to compare those. And when we compare those, the first 2 terms did match. If we wanted to get them to match more terms, we could have just used higher degree approximations of the original sine x and cos x. In 3D, we were going to find sine squared by taking our 3rd degree for sine and squaring it. So if you write it out twice and multiply it out, you end up getting what's in the box there. And then we wanted to, in E, we would do a cos squared by taking the 4th degree for cos and squaring it. This one got a little messy because you had to distribute three things through, but you end up getting this line here after you neaten it up. Now we wanted to approximate sine, get a polynomial for sine squared plus cos squared. So take your answer from D, add it to your answer from E. And that would end up giving you what we have on the bottom there for F. Now, remember this was built with Maclaurin polynomials, which means they're centered at x equals 0. It should be a good approximation when x is close to 0. And if x is close to 0, this polynomial would be pretty close to 1, which is something we know that sine squared plus cos squared should equal. Going over to 4, we wanted to find a 15th degree for sine x cubed. So put x cubed into our sine x and neaten it up. And we end up getting this here. In 5, from the graphs, the higher the degree, it should match the function longer. So the one that looks pinkish is the b. So b should be the highest degree one. That's why that's the sixth degree. The purplish one is A. That one is like the middle amount of matching. That should be the middle degree. And then C, the blue one, matches for the least amount of time. That should be the lowest degree. Another graph one. B did not match for as long, so that was the lower degree. A matched for longer. And then in 7, we wanted to do a limit. So take our Maclaurin for cos, and I just wrote out some of the terms and put dot, dot, dot. So we want to do 1 minus that whole thing, so the minus distributes, and we get that new numerator with the 1's gone, so this line here. Then divide everything by x, so the powers go down. And now that we don't have x in the denominator, now you can do direct substitution, and we get this limit as 0. You actually saw that this limit came into play when proving the derivatives for sine and cos. Probably haven't seen it since then, but you have seen it once in your calculus career. So we saw in this homework several of the big ideas, that our polynomials are good approximations when we're close to the center. We can get new polynomials by using the things we know and subbing in numbers, adding them, multiplying them, subtracting them, doing different operations. We could use the polynomials we know to evaluate limits. And the higher the degree we carry out our polynomial, the better it will match our original intended function. All right, we're going to start out today with coming up with a Maclaurin polynomial for 1 over 1 minus x. So it may seem strange, why would we want to work with this? But the whole purpose is eventually it'll help us get a polynomial that has a natural log in it as well. So there's a couple ways that we can do this. First, what I think is the harder way. 1 divided by 1 minus x, you could do long division. So we could ask ourselves, what times 1 gives us 1? So we'd put a 1 here. So that would give us 1 minus x. We would have to subtract, the 1's wipe out, and the change of signs gives us a positive x here. So then we'd have to ask ourselves, what times 1 gives us x? So that would be a plus x. When we multiply through, we'd get x minus x squared. We'll subtract. The x's wipe out. With the change of signs, we'll get a positive x squared. So then we'd ask ourselves, what times 1 gives us x squared, which would be x squared. This will give us x squared minus x cubed with a minus. This will give us x cubed here. And it would keep going on. We would have x cubed and so on after that. So that's a polynomial that represents 1 over 1 minus x. Now another way to think of it is think of our infinite geometric sum. If we have 1 over 1 minus x, that means that our a1 was 1 and our r value is x. So therefore, 1 over 1 minus x, you can think of it as starting with 1, multiply by x to get the next term. Multiply by x to get the next term, so we have x squared. Multiply by x to get the next term, we get x cubed, and on from there. So the geometric way is the quicker way to do it, but both of those give us ways to get that. Let's take a second, and we'll add that to our card. So on your card, under the e to the x1, we'll have 1 over 1 minus x equals 1 plus x squared plus x cubed plus dot 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 equals, we'll do our summation from n equals 0 to infinity. And notice this one, it's just x, and the exponent is matching the power, or the n value. So we'll just have x to the n. On the next slide, we have some graphs, and it might be easier to see them on here than on your paper. So the top right there is if we go out to a third degree, bottom left fifth degree, and then bottom right sixth degree. So notice it does seem to wrap the function better as our degrees get higher. But unlike sine and cos, it doesn't seem to wrap it infinitely because, for example, it never crosses that asymptote. So eventually in this unit, we will learn the idea of what's called an interval of convergence. That for these polynomials, some of them only have a certain window that they will continue to match the function better and better and better. And things like asymptotes will be issues for us. So we'll see that eventually in this unit. So even though it didn't match infinitely, still our big three ideas were true. At x equals 0, the center, it matched perfectly. As we moved away from the center, not as good of an approximation, but by adding terms, we could increase the quality of that approximation. So we can use this idea of geometric to find polynomials for things that are in that geometric form. So remember, we have a1 over 1 minus r. So as long as that spot's a 1, we can easily figure out the first term in the r. So this would tell us that a1 is 3, and our r would just be 2x. So our p3 of x, because we want to do a third degree polynomial, we would start with 3, plus, if we multiply by 2x, that's going to give us 6x. Plus, if we multiply by 2x, that'll give us 12x squared. Now, it asks for a third degree polynomial, so we need to keep going till we have an x to the third. So multiply by 2x again, and we get 24x cubed. And that would be our third degree polynomial that we were able to find just by recognizing the form that took, that it was the same as our infinite geometric sum. Here's a graph of our third degree polynomial with the original function. Notice it x equals 0 matches perfectly. Pretty close to x equals 0 matches good, but as you move further away, not as good of an approximation. Well, let's use this one now to find a third degree Maclaurin polynomial. What we need to notice is we don't have 1 in that spot that we need it. So first thing we're going to do is we're going to multiply by a half top and bottom. So we're going to redefine f of x so that it matches our form of an infinite geometric sum. This now tells us that our a1 is 1/2 x, and our r, just note it's normally 1 minus r on the bottom. So if we have a positive there, that means our r is negative. So we're multiplying by negative 1/2 x each time. So therefore, our p3 of x, we would start with a half x, and we're going to multiply each time by a negative 1/2 x. So next, we'll have negative 1/4 x squared. If we multiply by a negative 1/2 x again, we'll have plus 1/8 x cubed. And we stop there because that's when we hit third degree. So the next slide, we have a graph again. Notice that x equals 0, our third degree polynomial matches perfectly. If we're nearby the x equals 0, it's a quite good approximation. But as we move further away from x equals 0, that approximation is not as accurate. So we've seen the idea of getting new polynomials from old ones. We use sine to get cos. We used like the sine and cos ones to get things for sine squared, cos squared, our identity of sine 2x, things like that. Well, what we're going to do now is we're going to take that polynomial we saw earlier for 1 over 1 minus x, which is really just a geometric starting with 1 and multiplying by x each time, to eventually get one for natural log of 1 minus x. So if we take the integral of both sides, on the left, that's technically a u substitution that has a correction of negative 1. That's why the negative's out front. And technically, we should have natural log absolute value of 1 minus x. To resolve the absolute value, we need to think about at the center. These were Maclaurin polynomials centered at x equals 0. So when x is 0, a 1 minus x on the inside here would have been positive, meaning that our absolute value would just be whatever's inside, which is why it now has a parentheses. So there's some thought that led to that parentheses. We didn't just forget to put the absolute value in. It's because at the center it would be a positive inside. Over on the right side, if we take our antiderivative, this is going to be indefinite, so we will have a c on it eventually. A lot of times you'll see that c come first. So I'm going to do c first. And then we're going to have the antiderivative of 1, which is x, plus 1/2 x squared, plus 1/3 x cubed, plus ... If we know a point in our function, we can resolve that c. Well, an easy thing to always sub in is 0. So let's think about when we sub in 0, we'll end up having minus natural log of 1 minus 0. Well, natural log of 1 is just 0. So this says when we sub in 0 for x, we should get back 0 for y. If you sub in 0 for x, it wipes out all those terms with x's, and just c is remaining. And we want it to come back as 0, so for that to happen, we would need c to equal 0. So when we rewrite the next step, we're going to do two things. C is going to go away because c is 0. And also, we've got to get this negative over to the other side. So we're going to divide the negative 1 over, and remember c is gone now because it's 0, so we'll have negative x minus 1/2 x squared minus 1/3 x cubed, and so on. You also could write that with them over the 2, so you could do like negative x minus x squared over 2 minus x cubed over 3, and so on, as we've seen many of our other ones written. So what we're going to do is we're going to put this one on our card now, because this will give us a log, a natural log, which we could work from to find polynomials for other natural logs. Because the big idea is to use ones that we know to find polynomials of things that are somewhat similar to it. So on our card, let's put natural log of 1 minus x. We'll do equals that minus x squared over 2 minus x squared over x cubed over 3 ... equals our summation n equals 0 to infinity. And again, this is what we're putting on our note card. This should be our 5th one on the note card. Now note our sign is not alternating. It is always a negative. So we're going to have a minus that's always there. When n is 0, notice our exponent is 1. So it's 1 more than that. So we're going to want x to the n plus 1. And then notice that denominator matches the exponent, so it will be over n plus 1. Now in our summation notation for the one we started with, the 1 over 1 minus x, remember we had x to the n plus 1, or x to the n, so the antiderivative of that should go up to n plus 1 and divide by n plus 1. So that makes sense based on what we know about antiderivatives. So going to the next slide, we're going to see if we can use this polynomial now. So we want to use the 4th degree polynomial. So we're going to use this exact one right here. And we want to approximate natural log of 0.3. Well, natural log of 0.3, we're using natural log of 1 minus x to do that. So we need to think what needs to go in this blank here to give us 0.3, and that would be 0.7. So really, what we are subbing into our polynomial is 0.7 in order to find natural log of 0.3. So we're going to have minus 0.7, minus 0.7 squared over 2, minus 0.7 cubed over 3, minus 0.7 to the 4th over 4. And we stopped there because we wanted a P4, our 4th degree polynomial. And if we put that in, that would give us negative 1.11935 and change. If this was on a test, we would round to 3 places by our AP rounding standard. All right, we're going to see one more big thing in this video, but before we do that, let's recap what we know so far. Many functions can be approximated by polynomials. They can be complex. That's why having something that's a polynomial to represent them is helpful. We've seen sine x, cos x, 1 over 1 minus x, natural log of 1 minus x, and we also saw from the homework e to the x as well. There will be one more that we will eventually add to our card for arctan, but then that'll be all the ones that we'll memorize and then just work off of those. So the big ideas. Our polynomials are perfect matches at the center. If it's a Maclaurin polynomial, then that means it's centered at x equals 0. As you move away from the center, your quality of approximation is not as good. You can improve your quality by adding more terms to the polynomial. You can get new polynomials by taking the ones we know, and you can integrate them, take the derivative, we can add them, we can substitute things in for x, we can work with limits by subbing them in. So there's lots of different options. So working off these base ones that we know can allow us to find lots of new ones. What we're going to finish with is building a system that will work to find a Taylor or a Maclaurin polynomial in any case. Today we'll see it with the Maclaurin centered at 0, and then we will eventually expand it to work for any center. Because we're doing Maclaurin, that's why the things we're given are about f of 0, f prime of 0, f double prime of 0, and so on. So let's imagine we had some random 3rd degree polynomial. We've got C0 as our constant, C1 is the coefficient of the 1st degree term, C2 of the 2nd degree term, and so on. Since we know f of 0 is negative 1, when we put in 0 for x, that wipes out those last 3 terms. So that means we can now conclude that C0 should equal negative 1. Well, let's find our derivative of that 3rd degree polynomial. The constant C0 goes away. Derivative of C1x should just be C1, kind of like because 7x's derivative is 7. For the next term, the derivative will multiply the 2 out front, so we'll have 2c2 times x. And then we'll have plus 3c3 times x squared. Well, now they told us that f prime of 0 is 5. So if we sub in 0 for x in the derivative, all we'll have left is c1 to equal that 5. Well, let's see if we can keep going. Let's take the second derivative. The c1 is a constant. Its derivative is 0, so it goes away. 2c2x, its derivative will just be 2c2. And then the last term will have to multiply the 2 out front, so we'll get 6c3x to the first. Because f double prime is 0, f double prime of 0 is 1/5, we know that when we put in 0 for x, all we'll have is 2c2 remaining, and that should equal 1/5. Well, if we divide the 2 over, that means that c2 is just 1/10. So we'll carry it out once more because we still have to find C3. The derivative of the second degree, the 2C2 will go away, so we'll just have 6C3. So we're subbing in 0 for x, which there's no zeros to sub in for. So negative 12 should equal 6C3, or in other words, C3 is just negative 2. What we can do now is put that all together because we had the base form of our third degree polynomial. So P3 of x is really just our C0, which was negative 1, plus 5 times x, because that was our C1, plus 1/10 x squared, minus the 2 for x cubed. So what this tells us is that if we just know the value of n derivatives at our center, so in this case 3 derivatives at our center, then we can find the nth degree polynomial. So if you know your value of your function and the first 7 derivatives at that center, then we could do something like this to find the 7th degree polynomial. And that's basically what this next slide was just talking about, that if you know the value in n derivatives at a single point, you can build the entire, and let me add in here, the entire nth degree. But if you only know 7 derivatives, you can't go beyond the 7th degree polynomial. Well, let's see if we can make this even more general. We've got an original polynomial there, p of x, that goes on forever. It's got the dot, dot, dot. If we have f of 0, 0 goes in for all the x's, so most of those terms will wipe out. You're left with just c0. Well, we've done the work of taking the derivative for us like we did in the last one. So there's your derivative, all the exponents multiplied out by 1, or multiplied out front, the constant c0 went away. If we now do f prime of 0, so put 0 in for all the x's, we end up getting that f prime of 0 is just c1. Let's do that again. We'll take the second derivative. F double prime of 0, put in 0 for all the x's, we should get 2c2. So if we divide the 2 over, that means c2 is equal to f double prime of 0 over 2. Let's do it again. There's our next derivative, third derivative. F triple prime of 0, all the things with x's wipe out. So we would have 3 times 2 times c3. So in other words, that's 6c3. So if you divide the 6 over, that means c3 will be f triple prime of 0 over 6. And we'll go one more and then see if we can figure out the pattern. So if we do the fourth derivative evaluated at 0, we'd have 4 times 3 times 2 times c4. So that's the same as saying 24c4. Or if we divide the 24 over, that's fourth derivative at 0 over 24 is equal to c4. Well, let's think about what some of these denominators are. 24 is really 4 factorial. So this is really saying fourth derivative of 0 over 4 factorial would be what c4 is. 6 is really 3 factorial. So this is really third derivative at 0 over 3 factorial. Well, 2 is the same as saying 2 factorial. This is over 1. 1 is the same as 1 factorial. If we continue our pattern, 0 factorial is also defined as 1. So notice our constant term is really just over 0 factorial, and the constant term represents our function value at that center of 0. And it's the first derivative over 1 factorial. Actually, let me swing where I put these 1 and 0 factorials just to match the others. It wasn't wrong what I wrote, but we wanted the c1 and c0 solved for. So we'd want the 1 factorial there and the 0 factorial there, just to match better what we have below. So let's piece together this general polynomial now. So Pn of x should equal our C0, which we just found was f of 0 over 0 factorial, plus our C1 times x. We found C1 was f prime of 0 over 1 factorial, and then x. Our C2 was the second derivative at 0 over 2 factorial, and then that's times x squared. If we keep going, we'd have third derivative at 0 over 3 factorial times x cubed. And this could keep going. So let's write a general summation. We would go n equals 0 to infinity. We always start with the nth derivative. So I'm going to do fn of 0. So the 0th derivative, then the first derivative, second derivative, and so on. The x is always raised to our n value, and we are over n factorial. So what this allows us to do is I could give you any function, and if we wanted to do the Maclaurin polynomial, we could mechanically figure it out for like a 4th degree, 5th degree, any degree we want it. We've just got to take several derivatives of it and evaluate it at 0 and put those in our numerators. And that would make it really, really easy. Now, if you think about this, this works for our ones that we've memorized. So just to show you a quick example, let's think about sine x. Sine x, we know, is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. Well, where's our f of 0 over 0? Well, sine of 0 is 0. That's why that first term is gone. The first derivative of sine is cos. Cos of 0 is 1, and it's over 1 factorial. That's why we have this. Well, second derivative of sine is negative sine. Negative sine of 0 is 0. That's why there's no x squared term. The third derivative would be negative cos. Negative cos at 0 is negative 1. That's why we've got negative x cubed over 3 factorial. So notice, now that we know this, it actually checks out with the ones that we have memorized. For time purposes on your test, you're going to want those ones on the card memorized. Worst case scenario, if you know how to build out a general one like this, you could figure out what those ones are on our card. But again, from a time perspective, you'll want to have them memorized. That's it for this video. Have a great rest of your day.